Good afternoon to all. I hope you would have received all the materials for first three units. Since you don't have any doubts in unit 1, 2, and 3, I'll start the session today on unit number 4. If you're having any doubts, you can put in the chat box. So, global positioning system, unit number 4. First of all, I'll give you an outline of what is present in unit number 4. The topic starts with atmospheric effects, under which there are four different cases. One is phase and group velocity. Next is your ionospheric refraction, tropospheric refraction, then atmospheric monitoring. In this atmospheric monitoring, we are having three different things to be measured. One is ionospheric tomography, second one troposphere sounding, third one CHAMP mission. After the atmospheric effects, the most important design where we get variations of your phase offset has to be taken into consideration, which is antenna phase, center offset, and variation. We'll be seeing on the antenna phase, center offset, and variation, and last would be your multipath effects. So when we use an GPS receiver or a GPS system, what are the factors to be considered while designing and eliminating them during the retrieval process? So that is what this unit deals with. So to determine the phase and group velocity, we should be familiar with the first parameter called as phase and group velocity, which comes under your atmospheric effects. So our GPS receivers or your GPS signals all lies in our electromagnetic band, or it uses your electromagnetic waves. So these electromagnetic waves are waves that satisfies our Maxwell's equation. So the Maxwell's equation plays a major role in electromagnetic fields. So for this, we need to determine the every signal's phase and group velocity. So a GPS signal, whatever is being transmitted or being used, has its own phase and group velocities, which can be determined as here. A single electromagnetic wave propagating in space with wavelength lambda and frequency f, then its phase or phase velocity can be obtained as the multiplication of the wavelength with its frequency. So VPH represents your velocity of the GPS signal having an electromagnetic frequency. Lambda is the wavelength and f is the frequency. So we get the phase velocity as VPH is equal to lambda into f. For a GPS receivers, the carrier waves are two, L1 and L2. So if these two are being propagating with a velocity, then obviously we'll get a group of velocities to be traveling with different frequencies. So L1 will have a different frequency, L2 we have a different frequency as we had seen in the earlier classes. So for this, the propagation of the waves also will be in electromagnetic in groups. So thus we can find the group velocity also, which is minus df by d lambda into lambda square. So f is your frequency, lambda is your wavelength of that particular GPS system wavelength. So the propagation of the resultant energy, which is defined by the group velocity, is given as VGR is equal to minus df by d lambda into lambda square. So this velocity is always considered for GPS code measurements. When you go for measurement of your GPS, this GPS group velocity plays a major role. So a relation between the phase velocity and group velocity is necessary to determine this code measurements. So which is given by dVPH, which is your differentiated phase velocity, is given as f into d lambda plus lambda into df. So we are going to differentiate. So now after differentiating, we are rearranging this equation. We are rearranging it. So when we rearrange, we get df by d lambda. In terms of df by d lambda, we need to rearrange. So accordingly, when we do that, we get 1 by lambda times dVPH divided by d lambda minus f by lambda. And we know that group velocity is minus df by d lambda into lambda naught square. So we get, when we substitute this in this equation, we get this df by d lambda. We need to substitute in group velocity. When you substitute that, we get 1 by lambda dVPH divided by d lambda minus f by lambda into minus of lambda square. So substitute that. When you substitute that, lambda divided by lambda square divided by lambda, we get lambda. So minus will remain as it is. So remaining will be dVPH divided by d lambda plus f lambda f by lambda into lambda square. So lambda and lambda will be moving out. So we get plus f lambda. So on rearranging this, we get group velocity as, in terms of phase velocity, as VGR is equal to minus lambda dVPH divided by d lambda plus f plus f lambda. So this is your equation, group velocity. So finally, the Rayleigh equation is that we know what is this f lambda. So f lambda is the phase velocity. So phase velocity minus lambda dVPH divided by d lambda. So this is your relation between phase and group velocity. This phase velocity and group velocity are equal in non-dispersive media, and they correspond to the speed of light in vacuum. So they travel with the speed of light, which is approximately 2.99998 into 10 power 8 meter per seconds, which we write it as approximately 3 into 10 power 8 meter per second. So the wave propagation in a medium depends on the refractive index also. So generally this propagation velocity can be obtained from the below derivation that we'll see. So when we apply this, we get V is equal to C by N. The wave propagation in medium depends on the refractive index, which is N, and generally the wave's propagation velocity is obtained from this equation, which is V is equal to C bar N. C is the velocity of light. So applying this to the phase and group velocities, the appropriate formulas we get it as V phase. When we want to find phase velocity, it becomes C divided by N pH. When we want to find group velocity, it becomes C divided by N gr. So differentiation of the phase velocities with respect to wavelength for this equation becomes dVph divided by d lambda. dVph divided by d lambda is equal to minus C n square pH into dn pH divided by d lambda. Now substitution of the last three equations in this, which is the above equation. You know, Vph is C by NpH, and we know VGR is C by NGR. So this dVph by d lambda, what it is? dVph divided by d lambda is your VGR. Substitute here. VGR is equal to C by NGR. Substitute here. Then we can rewrite the equation as this: 1 by NGR is equal to 1 by NPH into NPH is common. So taking that common outside, we get 1 plus lambda 1 divided by NPH into dNPH divided by d lambda. So where C is common for all, so we remove C outside. C becomes a constant. So this equation can be otherwise written as this also. So refractive index of the group velocity depends upon the refractive index of the phase velocity into 1 minus lambda 1 by NPH into dNPH divided by d lambda. So this is an expression in terms of refractive index. So then the modified Rayleigh equation will become, which is this equation will become NGR is equal to NPH minus lambda dNPH by d lambda. This equation. Modified Rayleigh equation, where d lambda by lambda is minus df by f. This d lambda by lambda is always minus df by f. And substituting this in the above equation, we get refractive index of the group velocity is equal to refractive index of the phase velocity plus f into differentiated refractive index of phase velocity divided by df, differential frequency. So this is about the phase and group velocities. Let me check, see for any queries. Next is the ionospheric refraction. When a signal is being sent from a satellite to the Earth station or to the receiver, the signals get scattered away or refracted away due to the various layers which are present about 50 kilometer to 1000 kilometer above the Earth's surface. So, which results in a dispersive medium. A dispersion occurs with respect to the global positioning radio spectrum signal. So, due to the various layers being present, the ions whichever is being present in the ions which are present in the atmosphere tends to reflect or observe the signals quality. So that refraction is to be considered. So a series of approximates has to be determined by using some coefficients called C2, C3 and C4 that do not depend only on frequency but also on the quantity, energy bits per second. So where Ne represents the number of electrons per cubic meter along the propagation path. So with this we can find the Np, which is a refractive index of phase velocity, which is given by 1 by f1, which is c1 by f1 plus c2 by f2, f square, c1 by f power 1 plus c2 divided by f power 2 plus c3 divided by f power 3 plus c4 divided by f power 4 till the last expression. So using this approximation by cutting of the series expansion, the quadratic equation can be written as 1 plus c2 divided by f squared. And when we differentiate this, we get d and pH is equal to minus 2 c2 f cube f power 3 into df. And for this approximation of quadratic term, we get the group velocity as 1 plus c2 divided by f2 minus f2c2 divided by f3. Or in other words, after simplification, we can write refractive index group velocity ngr is equal to 1 minus c2 by f square. The group and the phase refractive indexes deviate from unity with opposite sign. So the relations are this. If you have a Earth surface, you consider this as the Earth surface. This is the object O, and we have a satellite which is present in space. which is about 36,000 kilometers above from the Earth's surface. And in between that, we have Earth's surface extending in the form of ionospheric region. So I view a point which is IP on the surface of the Earth. So due to the relation of NGR greater than NPH, which is group velocity is always greater than phase velocity, we'll get the group velocity will be always less than phase velocity, because this follows a relation of positive. The electron density, whichever is being present in this, is considered to be as positive. So we get this relation. So as a consequence of different velocities, a group delay and a phase advance occur, or you can call that the GPS code measurements are delayed and carrier phases are advanced. Therefore, an appropriate pseudo range are to be measured, which is of too long, and the measured carrier phase pseudo ranges are measured at very short hours. So code pseudo range will be very longer, and the carrier phase pseudo range will be very shorter as compared to the geometric range between satellite and receiver. The geometric range between the satellite and the receiver determines whether the pseudo ranges are too long or whether the carrier phase pseudo ranges are too short. So the amount of difference in both the cases of pseudo ranges, code of measurement of code pseudo ranges and carrier phase pseudo ranges would be C2 is equal to, where we have seen that this C2 will be minus 40.3 times of NE. The geometric for ionospheric path delay. Next is the Firm's principle, where we are going to measure the ranges. So the measured ranges according to Firm's principle is that S is equal to integral of n dot ds. So initially we set this n is equal to 1. The geometric range S0 along the straight line between the satellite and the receiver can be set initially as n. So here this is a straight line initially between the satellite and the receiver. It could be taken as 1. So when we take that, this will become S0 at the initial stage. It will become integral ds. No. The difference between the measured and the geometric range is always called ionospheric refraction. The difference between this during the initial metric, geometric, and the measured. gives the ionospheric refraction. So difference of ionospheric is equal to no, the difference of ionospheric refraction is given as surface integral n dot ds is equal to surface integral ds naught, which may be written for a phase refractive index nph from substituting the value of n. So n is your refractive index. It is 1 plus c2 by f square, which is this. N is 1 plus c2 by f square. For quadratic equation of the series expansion, n is equal to 1. So we get n is equal to 1 plus c2 by f square into ds minus integral ds naught for phase representation. So for phase refractive index nph, can calculate this due to phase velocity, and due to group velocity we get a result of group refractive index, which is ngr, which is n will become 1 minus c2 by f square. So 1 minus c2 by f square into ds minus integral ds naught. This ionospheric refraction due to group velocity due to phase velocities. So next is that a simplification method to obtain the integration of the first term. In the case of 1, so in the first term what do we have? We have phase velocities ionospheric refraction is surface integral 1 plus c2 by f2 f squared into ds minus ds naught. For group it is integral 1 minus c2 by f square into ds minus integral ds naught. A simplified version is that we are going to allow integration for the first term, and then the formula becomes this. For ionospheric refraction due to phase, c2 by f square into ds naught, and for group minus c2 by f square into ds naught. So this c2, we have a formula for that c2. It is the amount of difference is same in the cases of both phase and group, which is minus 40.3 ne, that we are going to write it here. So if you substitute minus 40.3 into ne in phase ionospheric refraction's phase velocity or phase refractive index, we get minus 40.3 divided by f square integral of ne ds naught. Whereas for group it becomes plus, so minus into minus plus 40.3 divided by f square integral ne ds naught. So this can be substituted for determining the total electron content. How much amount of total electron content is present in the ionosphere can be easily determined by ne ds naught. So this will be equivalent to your TEC. TEC is your total electron content in this surface. So I can write the equation. Ionospheric refraction due to phase velocity as minus 40.3 f square TEC, and for group velocity it is 40.3 divided by f square TEC. So how much is this TEC? So the TEC is that it is the electrons present per meter square is 10 power 16. 1 TEC is equal to 10 power 16 electrons per meter square. For every meter square in the Earth's surface, we have 10 power 16 electrons. So due to which refraction occurs. So keeping in mind all these things, we need to design an appropriate GPS system. So now we are going to take an example of some codes. So which we are going to take it as CA code, codes acquisition codes, which has a delay of, for example, 0.16 meters. The thing is that we are substituting that 1 TEC unit. So then it becomes 0.16 meter. So the total electron content along the signal path between satellite and receiver is this. The integral is assumed to include electrons in a column with a cross section of 1 square meter and extending from the receiver to the satellite. So since it moves in a vertical direction, we call it as total vertical electron content. We move from the Earth surface towards the satellite, which is vertical. So we call this as total vertical electron content or TVEC model. Sometimes this TVEC is otherwise called as total overhead electron content also. So this TVEC, if introduced, it requires satellites to be working at zenith algorithm or the zenith controlling structures. So for arbitrary lines of sight, the zenith angle of the satellite must be taken into consideration. So the zenith angle will be always this. For phase velocity, ionospheric refraction will be minus, this is your zenith angle, minus 1 divided by cos z dash 40.3 f square TVEC, and for group velocity the ionospheric refraction will be 1 divided by cos z dash 40.3 divided by f square TVEC. So if the path in the ionospheric length varies, if the path in the ionospheric length varies with a changing zenith angle, these two quantities differ only with respect to signs. You can see, you can verify the phase velocity and the group velocity differs only with respect to sign. So introduce, we are going to introduce a model for representing this. It's only plus and minus is the difference. So we are going to introduce a notation for the positive amount of ionospheric influence on a measured pseudo range that allows the omission of subscripts pH or gr. Okay, so we are going to introduce as plus del ino and minus del ino. So remaining is all same. So we can replace this by plus. If it is plus del I ionospheric refraction, it is your group velocity. And if it is minus del INO, we call it as representing your phase velocities. So for phase, the ionospheric refraction is always minus del INO. So where this del INO is equal to 1 divided by cos z dash 40.3 f square TVEC. Whereas when you write in terms of plus del INO, we get plus of 1 divided by cos z dash 40.3 f square TVEC. So this is your ionospheric refraction model. So just representing instead of pH as phase or GR as group velocities, we are writing in terms of signs, positive sign and negative signs. So next is a what we are going to do is that we are going to do a model with this zenith angles. So a single layer model with the assumption that all free electrons are concentrated in infinitesimally thick spherical shield at a height hm and having some ionospheric points. So we get the value of the ionospheric refraction from sine z dash is equal to Re divided by Re plus Hm sine Z naught. So what is this Re? Is that Re is the mean radius of Earth. Hm is the mean value for the height of ionosphere from the ground surface. Z dash, as we had seen, Z dash in the previous is that Z dash is the zenith angle at the ionospheric point where the person is present. And Z naught is the zenith angle at observing point. Okay. You can see that here. We have a point here, this IP point or the intermediate point. You can see in the diagram. We had said that we have an object here, we have a satellite here, and IP is the angle being created. We have IP, a point where ionization appears. So the angle which is being formed from the point IP to the satellite is Z dash, which you call a zenith angle, and the angle formed from the mean radius of Earth. So from that point to the satellite has Z naught, which is your observed zenith angle. Z naught is the zenith angle at the observing site, Z dash. So this zenith angle Z naught can be calculated for a known satellite position and approximate coordinates for the observation location. So for example, for HM, a value in the range of 300 kilometer and 400 kilometer is typical. So if you want to find the ionospheric effects from the Earth's surface, the ionospheric height of about 300 to 400 kilometer is a typical range where we can get good efficiency or a design. Now let us see the consideration of the satellite. The height is only a sensitive issue for low satellite elevations. The change of range caused by the ionospheric refraction is restricted due to the determination of TSA's total electron content. However, the TEC itself is a fairly complicated quantity because it depends upon sunspot activities also, which is 11-year cycle. So the sunspot is your 11-year cycle approximately. That depends upon seasonal, diurnal variations, and the azimuth angle of the satellite and the position of observation site. Depending upon all this, only the ionospheric refraction will occur. So, what are the advantages or the pros which is being present in the ionospheric refraction? So, the advantage of an ionosphere free combination is that the elimination of ionospheric effects. If the ionospheric effects are being removed or which are being minimized, then we may account to an approximately increase of 40% of the efficiency of the signal to be propagated from the satellites to the appropriate users or the receivers. So remember the derivation that the term ionosphere free is not fully correct because we cannot make ionosphere to be free fully. So for that, lot of research is going on for making calculations of this ionospheric effects, and that can be minimized at your receiver's computation. So in the year 1991, Brunner and Gu proposed an improved model to account for the higher order terms arising from the series expansion of refractive index of the total electron contents, the geomagnetic field effects, and the bending effects of ray paths. So, is there any queries for this ionospheric? Can you check in the chat box? I'll give you 2 or 3 minutes. For any queries, you can type in the chat box. Okay. Any doubts or queries? Let me see in the chat box. So if there are no queries, I'll start with the tropospheric refraction. So the tropospheric refraction is an important concept or important parameter to be noted in order to have a good GPS signal sharing information. So where we have the Earth surface as in this diagram. So Earth surface, we have an observation satellite, we have an observation site. So from this Earth satellite, to a distance of about approximately 11 kilometers, we have a wet region, and above that, approximately 40 kilometers from the Earth surface, we have the dry region. So the region from the Earth surface till 11 kilometers, we call it as wet region, and above that we call it as the dry region. So due to this wet region and dry region, we may get an effects or delays in the path. So which results in tropospheric refraction, tropospheric path delay, and simply tropospheric delays, which are being occurred due to the non-ionization part. So whatever we had seen in the previous is the ionized parts. And apart from that, due to the atmospheric conditions, we have a non-ionized parts, which we call it as tropospheric refraction. So the effect of neutral atmosphere, that is the non-ionized part, is denoted as tropospheric refraction or tropospheric path delay, or simply we call it as tropospheric delay. This name is given slightly incorrect, though it excludes the stratosphere, which is also another constant of neutral atmosphere. So, however, the dominant of contribution of troposphere explains this choice of the name. Though we have stratosphere also, but the dominance of the stratospheric effects are very much lesser compared to the tropospheric effects. So only this name is being given for this, which is tropospheric refraction. So the neutral atmosphere is a non-dispersive medium with respect to radio waves up to 15 gigahertz. So up to 15 gigahertz, we will not experience any tropospheric effects or tropospheric refractions. So thus the propagation would be of frequency independent. Consequently, a distinction between the carrier phase and code ranges are derived for different carriers of L1 or L2. If L1 is necessary, it's fine, or if L2 is necessary, so the different frequencies can be obtained with a distinction in between L1 or L2. So this tropospheric path delay is to be addressed when the frequencies are above 15 gigahertz. So that tropospheric delay will be always del tropospheric path delay integral of n minus 1 into ds. N is your refractive index. So this is analogous to the ionospheric formula. So the integration is performed along a geometric path of the signal. So then we get n trop as 10 power 6. So since we have the ionospheric, we had 10 power 16, which represents your 1 total electron content. So do not confuse that. This in ionospheric it is 10 power 16, whereas in tropospheric it is 10 power 6. Usually the measurement of megahertz. Since the transmission of the satellite signals having data will be done in megahertz, we take 10 power 6. And also the geometric path of the signal is also considered. So 10 power 6 n minus 1. So the tropospheric refraction will become 10 power minus 6 integral n tropospheric into ds. So now in a paper, Hopefield showed the possibility of separating this tropospheric into a dry region and a wet region. Okay, we have seen that the troposphere is having from height from Earth surface to 11 kilometers it is wet region, and from there from the Earth surface to the a distance of 40 kilometers we have a dry region. So he had segregated them as n tropospheric region into dry and n tropospheric region into wet. So where this dry, how do we determine this dry part and wet part is that the water vapor. The water vapor contains when it is dry, it is dry region, and when it is wet, we call it as wet part. So corresponding the equations can be segregated as 10 power minus 6 integral nd tropospheric refraction into ds for dry region, and for wet region del tropospheric of wet region is equal to 10 power minus 6 integral nw tropospheric into ds. So now the total will be summation of both. So 10 power minus 6 integral nd trop into ds plus 10 power minus 6 nw trop ds. And an empirical calculation can be done where about 90% of the tropospheric refraction arises from dry region, and only about 10% occurs from the wet region. So in practically modeling of these refractives are introduced and integration is performed by numerical methods. For example, we use the series expansions of the integranded methods. So next, the modeling of the wet region and the dry part or the dry region. With the surface of the earth can be given as n d trop is equal to c1 p by t, where p is the atmospheric pressure, P is the atmospheric pressure, T is the temperature in Kelvin, E is the partial pressure water vapor measured in millibars. So then the wet component can be found as NW naught of D trop, which is C2 E by T plus C3 E by T square. We will not find it for C1 because C1 will be having a value of P atmospheric pressure measured in millibars, and T temperature in Kelvin we take an absolute Kelvin temperature in dry region, and partial pressure of water vapor. So we get C1 as 77.64 Kelvin per millibars. Whereas for the wet component, we can find NW naught of tropospheric refraction C2 E bar T plus C3 E bar T square So C2 is minus 12.96 Kelvin per millibars, and for C3 3.718 into 10 power 5 Kelvin square per millibar. So where this C1, C2, C3 are empirically determined. Next is the problems that we face in modeling the water vapor content of troposphere. So what are the difficulties that we face is that a simple use of surface measurements cannot give the accuracy. So the water vapor content should be always monitored by using an radiometers. So these radiometers which have been developed or which are being designed should give us accurate water vapor contents or measurements. This is a difficulty in the measurement of tropospheres. Next is that these water vapor radiometers measure the sky brightness, temperature by using some radiometric microwave observations along the signal path that enables the calculation of wet path delay. And next is the accurate water vapor radiometers are expensive and experience problems at low elevation angles is required since the tropospheric zenith delay is amplified by the mapping functions. The difficulty in modeling the tropospheric effects is a big task, and the research is also going on for quite a long time. And one way where this solutions of this tropospheric refraction could lead is that it could lead to record the radio sound meteorological data, the water vapor radiometer measurements and statistics. All this gives us meteorological data for having a good monsoon or whether we have a bad monsoon, on which date, what type of waves in what wind perception. We can analyze all those data by analyzing the tropospheric effects. There is a major task and an appropriate model still to be determined. So till date, we are using the zenith delay estimation where the phase observations are slightly adjusted. In practice, this one zenith delay for each site and each session is estimated. However, it is good to have more than one zenith delay per session. So that is the advice for determining tropospheric refraction or minimizing tropospheric effects. So the major drawback is that elimination of the tropospheric refraction by dual frequency methods is not possible. So wherever you use only a single frequency method, you can eliminate or can minimize and measure the tropospheric effects. Whereas when you go for dual frequency where L1 and L2 are being combined together, the elimination is a big task. So research is still going on that. Next topic is atmospheric monitoring. Monitoring the atmosphere of the Earth. So in order to monitor the ionospheric effects, tropospheric effects. A system was developed as a diagnostic tool, which is called as ionospheric tomography. So, tomography is a development from the medical diagnostics tool, commonly denoted as computer tomography, that is used in image processing techniques for different applications. So, in GPS, this tomography is used in geodesy and geophysics, where monitoring and surveying is being done. So, referring to the ionospheric topography, the line integral of electron density, that is the total electron content, is measured over a large number of ray paths. That is a transition of the ionosphere. So, here this data is inverted to produce an image of the electron density in ionospheric maps. So all those ionospheric maps, data sets, image of the Earth where what do you call it? Ionospheric measurements or effects are done. I'll show in the presentation where all these things are being measured. Okay, image of the Earth at a particular location. So more GPS specifically, the total electron content that monitors using the satellite positions is possible. Example is a CODE code, Center for Orbit Determination in Europe, estimates the global ionosphere maps as an additional product. Center for Orbit Determination in Europe code estimates the global ionosphere maps as an additional product in the GPS system. So the main idea is to analyze the ionospheric residuals of dual frequency phases which contain the information on ionospheric refraction. This TEC is developed into a series of special harmonics adopting a single layers model with sun as fixed reference frame. For each day, a set of TEC coefficients is determined, which approximates an average distribution of the vertical TEC on a global scale. The global ionosphere maps contributes to improve the ambiguity resolution as demonstrated in the code processing. The Center for Orbit Determination in Europe. In this atmospheric monitoring, is used by the ionospheric physics, where these maps are used as an alternative source of information about the deterministic behavior of ionosphere that may determine which is correlated with solar and geomagnetic. So the ionospheric physics use these data, make iterations, find the solar parameters or the geomagnetic parameters, and give an appropriate data for monitoring the atmosphere. monitoring the changes in the atmosphere. So this GIMs, the global ionosphere maps, are based on a single layer model and the total electron density of the surface. So the TVEC model, which is your the total vertical electron content model we are going to see, which is your TVEC. So the TVEC model is a function of the ionospheric point expressed by geocentric latitude and longitude difference. So which can be obtained by summation n is equal to 0 to n max, m is equal to 0 to m, ANM cos m into del lambda plus BNM sin m del lambda into PNM sin beta. So this PNM sin beta are the normalized associated legendary functions of degree n and order m. So where n is the degree of order m. So this coefficients ANM and BNM are the coefficients of the system of the GIM, global ionosphere map. So those are those coefficients to be determined. Then lambda is your wavelength, which can be obtained by del lambda is equal to lambda minus lambda naught. So which is the lambda is your earth fixed longitude and lambda naught is the longitude of the sun. So if the scalar geographical reference frame refers to the mean sun, the geographic longitude of the sun may be written in a function of universal time codes or UT. So, and the geographical latitude of the sun is set to 0. So lambda naught will be 12 hours 12h minus UT, universal time. So the global ionosphere maps are generated on a daily basis by code. So the total electron content is modeled with a spherical harmonic expansion up to degree n is equal to 12. N could be a maximum special harmonic functions of spherical values up to n is equal to 12 and order m is equal to 8. So this refers to a solar geomagnetic reference frames. So if there are 12 hours being done, then per day we'll get two 12-hour sets that are being derived from the GPS data of the signal, which is given to the global IGS network or the data. Two 12-hour sets. So then the minimum value of TEC over the vertical can be calculated with an example. So the maximum and the minimum values of TEC for day 73 of the year 1996 are in the year 1996 measured value TVEC max beta comma del lambda. TVEC is minus 7.60 degree, 45.37 degree was at this position was 35.79 TECU. total electron content units. And similarly, the TVEC minimum beta comma del lambda was at 60.91 degree, comma minus 106.64 degree was 0.34 TeCu. The latitude, comma longitude. So this is your latitude, comma longitude. The mean TCU average from 1 GIM describes that the evolution of ionospheric activity in global sense and varies for a 28-month time span starting from 1995 January 1. Apart from the GIN, which is your global ionosphere maps, each and every country or union has different. For Europe, there is a regional ionospheric map based on some 30 European IGS stations. So 30 European IGS stations provides information about the TVEC contents. This is about the ionospheric tomography. Any questions? Let me see in the chat box. After the ionospheric tomography, we are going to see troposphere sounding. So, the reliable information on global climate change processes over future decades and for better weather forecasting either on near term time scale or a medium term time scale. The possible data of global and regional data records has to be monitored. So these data are used to accurately model atmospheric state parameters with high spatial So due to a network issue, I'll restart again from the tropospheric sounding. So the reliable information on global climate change processes over future decades and better weather forecasting on near term and medium term timescales in order to obtain the global and regional data records. So these regional and global data records are used to accurately model an atmospheric state parameters with high spatial and temporal resolutions. So water vapor is one of the most uh, significant constituents of the troposphere, where the parameters play a fundamental role with regard to weather and climate, since it has the capacity to transport moisture and heat throughout the atmosphere. So this water vapor's content is to be monitored at a different distances, where meteorologists have started to use a GPS as a low cost tool for measuring the water vapor. So the water vapors variations that we measure are being done by different meteorologists for measuring the atmospheric contents. So in tropospheric refraction, in the past we had a nuisance parameters. So that is being added with the signal. So during this estimation of the data, by using the tropospheric zenith delay, we can process it and eliminate those nuisance parameters. The dry component of the tropospheric information can be computed with high accuracy, whereas the remaining wet component or the wet system would be a function of the water vapor in the atmosphere. So the short periodic variations of the integrated water vapor gives us more information about the weather prediction, which can be used as weather prediction measures having an impact on the climate research. And specific example of the integrated water vapor as how it improves the climate research we'll be seeing in unit number 5 in detail. Don't worry. IWV, integrated water vapor system. So next topic is the CHAMP mission. So this CHAMP mission, which is challenging mini satellite payload, in short CHAMP, challenging mini satellite payload, which is used for geophysical research, and that started in the year 2000, which provides us a sufficiently long observation time to resolve long-term temporal variations in the magnetic field. So the gravity field, for example, the magnetic field can be easily determined by this CHAMP mission in the atmosphere. So some specifications of the satellites in this mission are: we can determine with an eccentricity of 0.001, with an altitude of about 300 to 470 kilometers, and an inclination degree of 87.3 degrees. Among the other equipments, the satellite has a dual frequency GPS receiver on board. The measurable refractional effects on GPS signal propagates through the atmosphere limb may be used to derive profiles for a variety of atmospheric parameters. So this ionospheric refraction is used A derivation of electron density in profiles between 60 kilometer and the champ orbital height. In conjunction with TEC measurements from a network of terrestrial stations, a comprehensive model of the ionosphere is possible. With a high resolution in space and time. The refractional effects in the atmosphere ranging from Earth's surface up to a range of 60-kilometer altitude gives rise to a profiles for meteorological parameters such as measuring the density, pressure, temperature, and water vapor. The refractional effects in the atmosphere ranging from the Earth's surface of about 60 kilometer, where the bending of signal path and the tropospheric path delays are being present. The measurements such as density of water, pressure, temperature, water vapor, integrated water vapor, all can be determined by using this CHAMP mission, challenging mini satellite payload. So the objective of this CHAMP mission is to determine all these parameters in near real time. With a practical orientation, the recording of all this can be done, such as density, pressure, water vapor, temperature. All these predictions can be done usually by this CHAMP mission for monitoring atmosphere. Predictions. So next topic is about antenna phase center, offset and variation, and multipath. So these two topics we'll see in the next class. So any doubts or queries, you can type in the chat box. Kindly await. I will be sending you the attendance form in chat box. You can fill that. And the students, those who are filling the Google form, will be given attendance.
Yeah, we still didn't get any links regarding attendance. Are you there, sir?
Check in the chat box. You can fill the attendance form.
Hello? Hello?
Hello, yes.
Yes, sir.
It is not showing, huh?
Not responding. Yes, sir.
Okay, you send me your register number. I'll put attendance.
Last time also like that only, sir.
I
I
think
think it was
for remaining people it is getting, but for you it's not getting.
it was showing sign in, sir. When we click it
Yeah,
sign
you
in,
should
it is not
sign in with.
responding.
Yeah, yeah. Then you reset your browser. Your browser is there now.
Yes, sir.
Uninstall that and reinstall it again. It may work. It will work from the next class onwards.
Now you can do attendance, sir.
I'll give you. You send me in WhatsApp your register number.
Oh, okay, sir.
Okay. Thank you all.
Thank you.